Okay, sounds like they can hear. Excellent. So I wanted to welcome everyone to our colloquium today. We have Kimberly Ennico Smith with us here. She got her PhD from Cambridge University, and then following that did a postdoc at University of Arizona and has been at NASA Ames since 2000. And is technically still at NASA Ames, but is here with us local in Boulder. So we hope to see a lot more of her in the future. She's been involved in lots of different instruments and missions as the project scientist on SOFIA, and most recently as the deputy project scientist on the VIPER rover, which we'll hear about today. So I'll turn it over to you, and thanks everyone.
Okay, thank you. Thank you for inviting me to speak with you, and this is such a delight to see eyes and eyebrows, the occasional nose and mouth. That's fabulous. Obviously, a talk about a NASA mission. I'm one of many on this mission, so I have the title of a deputy project scientist. All that just means is that I'm a scientist who occasionally speaks engineering, and I poke my head and ask lots of questions, and I'm always skeptical. But I'm delighted to share with you the story of VIPER, the Volatiles Investigating Polar Exploration Rover. And I've entitled it The Next Great Leap in Mapping Water on the Moon, which I will get to at the very end of the talk. So hopefully you'll hear me out. So again, speaking on many, it was not that long ago, it's only just a few decades ago, that how we thought about the moon was very, very different. So time warp yourself a couple decades past, and we did study it from the Earth. In fact, we even visited it, and we had samples returned. But the general consensus at that time was the surface was constant. There's a thin exosphere, a few trace elements, and it's bone dry, 100 parts per million. And perhaps this water is in the soils. Now that's 250 times drier than the Sahara Desert. So the moon was considered dry. I also want to point out, in the 1960s, there were a few intrepid scientists who wrote hypotheses about the presence of unique conditions at the polar regions of the moon that could act as a cold trap. This is an incredible lesson for scientists who put their ideas out there in the published work, which might not have been very popular at the time. So Watson, Maury, and Brown coined the term of cold traps, and they set expectations that the moon could harbor unique places where temperatures were cold enough and molecules could be trapped there. And I highlighted the solid phase, which will be collected at the coldest points on the lunar surface, and cold traps. There was another paper in 1979 about ice, but then the conversation went quiet for decades. Now, our knowledge about the unique geometry on the moon are these regions called permanently shadowed. There are places in our solar system, Mercury and Ceres and the moon, have these unique places where sunlight never reaches. And in the moon's case, it's due to its low obliquity. And at high latitudes, which means at both poles, the topography, the local topography, the crater rims, the high massifs, they create permanently shadowed regions. And there's a lot of it, 10,000 square kilometers of it. And what's curious is they exist on the large scales, the kilometer, to even potentially these smaller scales. So we have these permanently shadowed regions defined as a location on the surface of the moon where the sunlight has not shone. It's in permanent shadow. You may have seen this time-lapse video, which is put together from data from the Lunar Reconnaissance Orbiter, a mission that was sent to the moon in 2009 and still in orbit, has made global maps of the moon, especially its topography. And then we can work out which parts are in permanent shadow. So you can just find a place. This is looking at the South Pole Shackleton craters in the center. Just look at a place, and this shows how the shadows move at the South Pole of the moon. And hopefully your eyes can find a place where it's in permanent shadow. So let's look at this region a little bit more. So I highlighted a couple of names, Shackleton crater, Sputus, Marvin, de Galache, Shoemaker. And the permanent shadow regions are also correlated with, if they don't have sunlight, you think they'd be cold. So I'm just superimposing on this a map from the Diviner instrument in LRO, which mapped the surface temperatures. And indeed, blue here is showing very cold, 100 Kelvin, 75 Kelvin. Areas in permanently shadow are correlated with cold temperatures. And some of the basins of these craters are colder than the surface of Pluto, right, Kelsey? Colder than objects in the outer solar system. So the poles of the moon are an exotic place. So let's step out and understand what chemistry could be going on. So we have this teaser from 1961 with the Watson paper about lunar cold traps. We now have maps of the moon showing the temperatures on the surface of the moon. And what's interesting is that these temperatures, is a fascinating paper by Zhang and Page that basically looked at which molecules will stick around at cold enough temperatures. I get you to think about with the termination of volatile. I'm going to use this term a lot. So a volatile describes a molecule, a component that can easily go into the gas phase and escape. It's very volatile. It wants to get rid of it. However, when you're at very cold temperatures, you'll stick around. And would you stick around for how long? 1,000 years, million years, giga years? What's interesting with the Zhang and Page results is they looked at a variety of molecules that potentially could stick around on the cold surfaces indicated by permanent shadow on the moon. And if you're colder than 110 Kelvin, water will stick around. Water is the focus of this talk, but there are also a lot of other lovely volatiles that we want to see if they are in these cold traps. Another piece of the story has to do with neutron maps. So we've had orbiters around the moon. There's a lunar prospector that was in the 1990s, and we have LEND instrument on LRO, plus Apollo had neutron spectrometers on the surface for the Apollo landings. So we've been looking at what the story of the moon is from neutrons. Now, what's happening is neutrons are generated by the galactic cosmic rays. When they interact with something around their size, say a hydrogen atom, they'll lose some of their energy. These maps are showing the suppression of neutrons. The dark purple is indicating where there's a lot of neutrons suppressed. There's not many neutrons leaking out to the surface because they're interacting with something and losing its energy and setting off a chain of reactions. The interesting thing was that the polar regions of the moon, both the north and the south, show these higher levels of neutron suppression, which has been interpreted to be the indication of excess of hydrogen, because a hydrogen atom is a similar size to a neutron and would be an indicator. But that's not the whole story, because you can't tell whether the hydrogen is in the form of water. It could be in hydrogen, it could be OH, it could be a hydrated mineral. It's a good proxy, but not the complete picture of water on the moon. So to sum up the last decade, we, the scientific community, because I am far from a lunar volatile expert, the moon is now known to host 3 forms of solar system water. The endogenic, which means it's made on the moon, perhaps solar wind, hydrogen protons are hitting and interacting with the regolith, which has oxygen, making water or OH. Sequestered external, which means it's brought in by comets and asteroids and going to those cold traps, and also in situ, could be left over from the volcanic age of the moon's history. It started off with Carly Peters' paper, 2009, with the mapping of OH from the Chandrayaan-3 M-Cube instrument. We have the lunar L-cross impactor that hit the Cabeus crater in the South Pole and excavated, and we took spectra of it. And in order to fit the absorption lines, you needed water vapor and water ice. And L-cross to date remains the one and only bona fide detection of water in the subsurface of the moon, because we dug up a crater. We also have a reevaluation of the M-cubed data, where they're taking into knowledge from the LRO instruments and constraining where the water could be. And there is a latitude dependence, but there's also a diurnal cycle. There actually may be a water cycle on the moon. We've had reinvestigation of the Apollo rocks 50 years later. They are brought inside the chamber, and now the instruments in the lab are orders of magnitude more sensitive and have detected water inside the Apollo rocks. SOFIA, the infrared flying observatories, observed water in a sunlight region on the surface of the Clavius region on the near side. Perhaps it's water it's protected by regolith around it. And even just this year, a paper came out in January or February of the Chang'e 5 lander, who has now found water in a rock, and everything else that is around dry. So it may have been another indication of in situ water. So we have this evolving story, but we do not understand the concentration, the evolution, the dynamics. Theorists are ruling the conversation right now. Now we need the measurements to test those theories. And so surface measurements are critical, and we need to look at scales. So this is the motivation. Of course, if we find water on the moon, which we believe there's water on the moon, but to find it on the scales and how much of it is, and when did it get there, and how long why is it still there? It can be used for human exploration as well, radiation shielding, oxygen to breathe, water to drink, and fuel for rockets. So there's a lot of folks interested in lunar water. Now, this is also exciting in the field. Just in the last 2 years, Cannon and Britt have come up with predictive ice favorability indices. So this is an interesting take. So what they've done is they've combined different data sets, the Neutron Maps, those OH near IR spectral reflectance maps from orbit, UV reflectance maps, and they're trying to see where multiple data sets point to the same thing. But they've also included environmental effects like slopes and accessibilities, because if you want to go and harvest the ice, it should be easy to get to. So we have a roadmap, a guide. How caution, highly model dependent. Do they take into account the latest understanding of space weathering and gardening? What about the regolith thermal diffusion properties of how water interacts in soil? They're making some good guesses, but the data user beware. But knowing where water might be is only part of the story. Then you have the whole community who wants to mine the moon. Okay, because if you can live off the land, or you don't have to bring everything with you. But this is another interesting area about the need cases. The need for water to fuel n number of rockets is different than what the water is needed for habitat shielding. Maybe it's not cost effective to go mine a bunch of water because, it's difficult to get at. So there may be different need cases. And then scientifically, we have questions. So we might be interested in, are there monolayers of water on the dust? This could tell us about the history of the early solar system and bombardment and all our understanding of the cycle of water on the moon. But a mining ISRU, in situ research utilization architecture, might not be interested. So the reason why I'm bringing this up is that there has to be some sort of limit by which this is credible. And so there are several papers on the economics of water mining and volatile mining, and they all come to this 1% by weight criteria for which it's worth it. If it's much lower than that, it might not be worth it at all. So this plays into the design of our VIPER mission. So we've sort of established there's water on the moon, but we don't quite know how much of it is and how it's interacted, and we need some data. So the important bit is to start mapping. So the goals of the VIPER mission are to characterize the distribution and physical state. And we're going to look at water, but our instruments are capable of sensing the other volatiles. At the same time, we have a second charge, is to evaluate the potential return from in situ reutilization. So this is going after this 1% weight percent. If it's in much smaller quantities, it might not be something for ISU, but scientifically it still be very interesting. So, so this next great leap is to map these volatiles at the human, at the rover scale. And this is why we have a rover. We need a mobility asset on the moon. If we just landed, we would only get that sample in that one place. We would be back to the L-cross error, where we make a sample, we know there's a lot of water in one place, and we got to wait a decade and a half before we move the story on. Now, VIPER is kind of part of a whole resurgence of exploration of the moon. You may have heard of Artemis. Yes. So Artemis is the return of humans to the moon, but this time different than Apollo's. It's not like a picnic or a sortie, stay for weeks or months. I mean, the Apollos only last, the first Apollo 11 was less than 24 hours. Apollo 3 was 3 days. Apollo 17 was 3 days. So we have not spent a lot of time outside our magnetosphere. So there's a lot of learning to do. But VIPER is going to help with understanding the mapping for where humans might go for resource utilization. So where the team behind VIPER has been approaching the mapping charge with rigor and within the constraints of our mission. So it's not by luck. It's going to use a lot of geostatistical approaches that the USGS has been doing for decades. I mean, if you want to find where the gold is or where your mineral precious gem is, you learn by what's been done before. So the ultimate outcome is to develop this model for the moon, our resources. So this led to how the VIPER mission is attempting to approach the problem of making the first resource map on the moon. Actually, it's a first resource map on another celestial body. And a huge nod to the USGS who've been doing this on Earth. And one of the things is you start off with simulations. So we know that we've established that we're going to have a rover to get mobility. We need to sample a lot of area. So first of the question is, how much sampling do you need? So we did some simulations. There's the Monte Carlo simulations. Computer time is cheap. So you put in a random assortment of what the water could be like based on our knowledge from orbital assets. You put a hypothetical rover traverse on it, and you look at statistical correlations between at what point do you actually sample enough terrain such that you are statistically covering enough to show that we can say this area is dry, this area is wet. And so this has led to a science requirement that we have to sense a region of 10 to 15% per this area of interest. And this comes down to whether your rover path is spiral, zigzaggy, or a random walk. You also have to think about what else do we know about the moon. We're not going into it blind, but we don't know what we're also going to see. But the factors that control the distribution, it's the crater mixing. I mean, this is the dominant geological process. On that top meter of regolith is craters, impact cratering. And it's going to churn up the soil. So, work by Dana Hurley and her colleagues, have shown that the top meter of the regolith is expected to be patchy. Over the whole geological history of the moon, we're going to have, everything's going to be churned up, and there's going to be, the craters have a certain distance amongst each other from what we know at that scale. And so we want to be able to, see if the peanut butter is chunky or smooth. We want to sample a region that covering this 10-meter diameter crater. So we want to be ensuring that our maps that we're making is definitely covering this trade space of the 10-meter diameter craters. Another factor that we are aware of is this temperature. I mean, cold stuff will stick around. So although it appears to be a necessary requirement, it may not be the only one. And so we want to understand that better. So, and also the fact that the temperature variations are dependent upon this topography, the shadowing. And so the shadowing may change the temperature on the order of 5 meters. If you look over 5 meters over here, it could be a different temperature. And so we want to be sensitive to that. What's also quite interesting is I'm showing on the left another one of Paul Haynes' temperature maps of the South Pole. This is just showing the Shoemaker, Haworth, and Faustini region. And then superimposed on that is another compilation by Lee et al., who was looking at other data sets to see where UV reflectance is present. And on the right is a paper that talks about the UV reflectance, and in particular, how it rises in certain parts of permanently shadowed regions. So we have this intriguing picture that yes, we may have surface frosts determined by orbital assets that are looking at hundreds of meter per pixel kind of scale, but they're not always correlated with they're correlated with the temperature, but not all cold places have the water frost. That's what I wanted to say. Cold places have frost, but not all cold places have frost. What does that mean? So then you have another approach is about this whole thing of why the water ice may still be there. So we have this establishment of lunar cold traps, temperature's cold enough, water should stick around. So Matt Siegler and colleagues have been doing modeling about could ice be present for giga years? And in particular, what about beneath the surface? So up to now, we've had orbital assets telling us the story at the surface. But now we have a three-dimensional view of the story in which there is a prediction, the depth at which the ice sublation would be so small over geological timeframes that water should be there. So the VIPER mission is taking this as its guide. Caution, model dependent. Siegler and company do not take into account crater gardening at all. So I think the top 30 centimeters are going to be fascinating, but we have another guide, another road, a guide to the south, to the polar regions. But there's certainly a lot of interesting theories to test. Okay. So what are we going to do with this? So we have on the left is a zoom in model of this ice stability depth map. What we can do is do statistical approaches to understanding this. And this is how we're going about, we need to sample on these smaller scales. So what you do from a blind statistical point of view is you create something called a variogram. You can look at every point and you look at every other point with relation to it. And then you can plot a particular parameter and say, in this case, temperature, or say, in this case, ice stability depth, or say, in this case, hydrogen, or say, whatever your parameter you're looking for. And then you can plot it as a function of all the correlations, as a function of how far are you away from this. This is an approach that the USGS has been using to know whether, if I find gold here, what's my probability I'm going to find gold there? And you have maps about how minerals form and all that. In this case, when you just do it on our model that is using as our guide map, we have learned that how you do the statistics, when it starts to flatten out as you go further and further away, there's no correlation. But as you get closer and closer to the points, you start seeing correlations. When there's inflections, that means something's happening. We don't know what that is, but this has been an interesting technique to come up with a way to tackle a large area and do it strategically. Now, how large an area to characterize? So Hain et al. Has a very intriguing paper, and he and I were chatting this morning about it, that there is a prediction that PSRs could be on the order of centimeters in size. So no more just these kilometer-sized craters. You could actually have PSRs, the size of this desk, the size of this monitor. This is the theory, and it's very intriguing, and it kind of makes sense, but it also needs some observation. So one of the things we'd love to, with the data from the rover, is we're able to sample at these smaller scales to see how close these predictions are. So we're expecting significant temperature variation on the surface. We're now expecting them to have small scale temperature variations, and we may even come into the permanent shadow regions on small scales. Now there's an open question, do they also have water ice in them? Who knows, that's another variable, but lots to study. So what we did another statistical approach where we hypothetically say water is in this distribution, and then we have a different distribution here. And we worked out at what point does the barriers blend themselves together to go from wet to dry and all that. And we found that we needed to sample a decent size area. So our going in is the 3,800 square meters. This tells us when we start to blend with a nearby, not so adjacent dominant temperature range. So that was more about the surface. Now the vertical. If I haven't said it already, our rover has a drill. So we're going to do a vertical scales, but why are we doing the vertical scales? So on the left is shown from the Apollo missions that the lunar soil gets dense very fast. In fact, its maximum density may be around 50 centimeters deep. When you get deeper than that, it might be just difficult to excavate. On the right is a paper by Hurley et al. On predicting, because of gardening, this churning up on the surface. What's shown here is that the impact gardening, the bombardment of the surface, is going to change the ice. So the ice is kind of shown in the light gray, and after a giga-year, it's pretty much dissipated. So it's possible that this top part of the regolith will be desiccated. So we might need to drill deeper. So we have this intriguing notion that we can't deep too deep because we're going to hit rock. But we know that there's this interesting depth between 0 and maybe 30 or 0 and 50 centimeters that we don't know what we're going to find, and we might need to dig deeper. And then our current sense of things at depth is limited. Right now we have the Neutron Maps, and there's been radar and bistatic radar, but the uncertainty is behind that. So we don't quite know how to ground and bound the errors on our current depth percenting. And then how fine should we sample? So we think we're expecting between 20 and 50 centimeters depth. It's going to be anything, it's depending on where we are excavating, looking at the soil, where the impact gardening was, how old everything is, and the landscape. Maybe it's been affected by this, impact gardening has desiccated that top half meter. We also know that with the Neutron Maps, they seem to sense down to 1 meter, but we don't know, is it dry over wet? Is it wet all the way down? Is it stratified? Heck, it can even be deeper, but the neutron measurement should not have picked that up. The neutron measurement should only have really sensed that top meter. So on the right has been some more Monte Carlo simulations where we've adopted a particular water profile. So concentration increases to the right. So we start off with dry. The red line is the model. And we get wetter as we go below, because this is what we're thinking on seeing. And then you run a couple of simulations about how can you distinguish it. So this led to the design of a drill that takes data in bytes. We go down 10 centimeters at a time, then we look at it. Then we go down 10 centimeters at a time. Then we go down 10 centimeters at a time. We have the ability to adjust it, but this is giving us an indication that we can't go all the way down in one go. We do need to really sample. Vertical sampling a little bit finer. So to sum up on this part of the talk about the drivers behind the mission is essentially our science traceability matrix. We have all our sensitivity, coverage, density, length scales, area coverage, variability, vertical coverage, and vertical sampling, which led to the design of the mapping mission and the instrument selection. So let me segue into telling you about the mission. I mentioned already it's a rover. It's a cute rover. And it's going to be in shadow, so it's got lights. This rover is going to drive in the dark. Now, we are in communication with LRO, which is still in orbit around the moon, and they're going to hopefully take a picture of us while we're roving around in the dark. We don't know yet whether they're going to see our headlights, but you know, we got to try. But anyway, so we have cameras and lights, and we even have lights in the wheel wells, because we'll be driving around terrain that we haven't mapped at the scale. I mean, our knowledge of the moon, luckily with LOLA, when it passes over the, LOLA is a laser altimeter on LRO, the orbital mission. They measured the topography, and we got basically 5-meter resolution at the poles. It's more like 20 meters at the rest of the moon, but 5 meters at the poles. So our maps, in terms of where things are high, is on the 5-meter scale. Our rover is smaller than 5 meters. So we are navigating in unknown territory on the size of our scale. The other interesting thing is we don't really know the nature of the regolith. I was chatting with the grad students over lunch, and the whole thing is that top 30 centimeters is going to be so churned up that it's going to be like quicksand and we're going to get stuck. So this rover has been designed to be extremely mobile. It's got, the top right is showing sort of what it calls a squatting move. So it can go up and above different obstacles. We also are practicing doing swimming to go up and tread out through this regolith. So there on the bottom is a laboratory at Glenn Research Center, and the different parts of the mobility system are being navigated. So yeah, this is a very different type of rover designed to hopefully work out the unexpected as best we know. What else is going on? I mentioned we're at the pole. I didn't mention that we're driving the rover from the Earth. So we're tele-driven. And this is interesting because the sun might not get above the horizon very much, but neither will the Earth. Since we're only tele-driven by communication to the Earth, there are times during the mission where the rover has to park and wait for the Earth to get above the horizon again. So we have those, we have to factor those in our mission. I also mentioned that we're going to be going in and out of shadows because of this terrain at the poles where shadows are hundreds of miles long. What's shown here is an animation of one of our potential rover paths. The dark is the shadow and the lighter gray is the sun. The shadows are moving at the same speed as our rover. Our rover is solar powered, and we are going to be driving mostly in the sun with the shadow behind us and making sure we get to places that are in shadow and escaping out of the shadow before our batteries run out. So it is a very challenging design to drive a rover on the poles of the moon and have it be solar powered. Another thing I should mention, it's cold there. I think I mentioned it was cold there. But what's interesting is since we're solar powered and we sit up about 1.5 meters off the ground, there's some parts of the rover that get direct sunlight. They're going to be basking in the sun around 300 Kelvin. And then there's going to be cold parts that when we drive into these permanently shadowed regions to look for surface frost, we're going to be at 40 Kelvin or 50 Kelvin. So we have a huge range of temperatures to deal with. The heart of the mission is the science instruments. We carry an imaging science suite, which are navigation and hazard cameras. We have a neutron spectrometer system. That's our bloodhound that's going to hunt out the hydrogen signatures and tell us where there's favorable places to go next. We have the nervous instrument, which is a combination of several spectrometers and a camera that looks down at the belly of the rover. We have a mass spectroscopy to look for the gas phases, the M-Solo instrument, and we have the drill. So the Viz suite is more than just helping the drivers drive. It will be of interest to some topography and geometrical on the small scales. So one thing for Paul's interest is when we take our panorama, we're going to make DEMS, digital elevation models of the local terrain. We can then use those at the 1 meter or sub 1 meter scale to then look at the lighting conditions of where we've roved over. And then we could perhaps correlate what we might have seen with the topography at those times. The cameras look down the belly out towards the side. We may be able to do some rock size distribution. If you're interested in wheel soil interactions, does it, rub up against the wheels or it gets stuck? And then the U2 rovers the Chinese rovers on the moon have had some interesting experiences with regolith getting stuck on their wheels. And will we have the same thing too? That has some implications for future rover designs. And lots more other science. Okay, what else? Okay, the neutron spectrometer system sits up high and is searching about 1.5 meters in front of the rover. And it has 2 detectors to measure the thermal and the epithermal neutrons. There, as I said, galactic cosmic rays are coming down. There's a neutron flux leakage. This is detecting how many neutrons. And if there's not many, there might be the presence of ice or hydrogen at depth. So this is the culmination of many years of work of running a neutron spectrometer on a rover in the field through analog missions. And so there was Rick Elphick, who's the PI, has done a lot of work on this instrument out in the field. And this is some simulated data. And during the actual mission, we will be plotting the data against model predictions of dry over wet, and then using this to dynamically determine a water equivalent hydrogen map and an ice burial depth. So I might be jumping ahead here, but these are key diagnostic tools that will help us alter our rover's path based on the knowledge we're learning. So we have our guide map of the ice stability depths with the caveat that's model dependent, will tell us where to go. We're going to be roving along and taking data, and we're going to be checking, is that checking the model? If it's very different from the model, we may actually change our approach. So that part is, the NSS is key to helping us get those first ground truthing of the ice stability depths. The nervous instrument has a camera on it with multiple LEDs. I haven't gotten to showing you the drilling, but one of its places is to image the drill pile. So the drill's going down in bites and the pile is coming up. This gives us context of the angle of repose, and we can determine some properties of the regoliths. It also has 7 colors to help with mineralogy. These are spectra from lunar samples, Highland and Mare, and the vertical lines are showing our wavelengths of sampling, so you can kind of distinguish different mineralogies. Of course, the heart of Nervous is this infrared spectrometer. It's going to be hunting out the volatiles through reflectance spectra from a lamp illuminating the surface, and we're going to see the regolith plus hopefully the volatiles. This is just showing a couple of species. And we have a radiometer with 4 channels covering 6 to 25 microns, this would give us the surface temperature. So we might have the first surface temperatures on the order of decimeter scales, at least over the tens of kilometers that we've roven. And the NERVIS instrument has all the bore sites or the fields of view superimposed on each other. So whatever the aim camera, the camera is seeing is where also where the radiometer and the spectra are looking at. The M-SOLO is a mass spectrometer, and it will trace the ion and molecular inventory over 1 to 70 AMU. The instrument is capable of going out to up to 100 AMU. And if you are a spectroscopist, Krypton, which is shown here on the right, this is one of their test samples. That's at 83 AMU. This is all done for calibrating the higher mass end, but it's got the ability to look at the 1 AMU plus or minus. So this is extremely interested for those who are interested in isotopes. So we can tell you the difference whether you have HD and H2 or H2 18O versus normal oxygen, H2 16O. So what's shown here on the right is some data from a lab test with the Trident Drill and M-SOLO, where they're looking at when the pile collapses, they're starting to see a increase in the water or the 2 AMU, which is hydrogen, so they can distinguish between the species. Oh, I should be mentioning that all these instruments are going to be flying on missions prior to VIPER. These are these CLIPS missions, the Commercial Lunar Payload Services. NSS is flying on Maston's 19C mission, and I think Prime 1 as well. NERVIS is flying on Peregrine 1, which is going off this year. M-SOLO is going to fly on Peregrine 1 and Prime 1. These are names of missions. So the same instrument or a sister instrument will be sent to the moon, and we're going to learn how those instruments behave on the moon prior to VIPER's launch. Getting into drill, the Trident Drill, which is made by Honeybee Robotics. A lot of science here, but also, of course, it's our only way to do the really depth, the subsurface assessment. So one of the things is to look at the cuttings cone, angle of repose. It will also press down into the surface, so we could look at the thermal bearings of the regolith in the places where we can go. Drilling is expensive on this mission. Drilling is 4 to 8 hours of mission time. This is a very challenging mission where the shadows are moving and the time and the comm is moving. So drilling is not something you do all the time. We're in strategic places and strategic times in the mission, but we could put down the footpad. We could probably do some extra tests. We have some temperature sensors in the drill bit, and this is key. So this will at least tell us how cold that first 1 meter is. And this will be the first of its kind to help anchor those models. And then there's also a sensor at the very, very bottom of the drill. And the anticipation is, can we use the drill data to distinguish the possible ways water could be hiding in the soil? So so the Trident Drill will fly this year on the Prime 1 mission, and M-SOLO will be watching it. So that two combination will have a test run on the moon later this year, and it's going to a polar region, but it's a different place than where VIPER is going. So how are these instruments are dynamically and interrelated, and 3 of the instruments, NSS, NERVIS, and M-SOLO, are used during the prospecting aspect. So we'll have things like the scientists at the Mission Science Center will be looking at the real-time data. And we could see something like this. The rover has just driven over what we think is frost. And how do we tell that? Well, because the surface temperature just dropped. And we also see that the band strength of the water from the infrared reflectance has gone up while the temperature is going. And we've also noticed that the neutrons are going down, which is indicating more hydrogen. But then as we got further along, the surface temperature goes up, but the neutron counts stay low. This will be a distinguishing feature that we're looking for to see whether we're seeing surface ice or buried ice until we drill. So we're going to be watching different parameters and then flagging, okay, candidates for drill, and then our geostatistics are going to go, okay, let's do all this variogram. Where are the probabilistic places where we should drill next? So drilling is interesting. The drilling will use the Nervus, the M Solo, and the Trident. And what's shown here on the right is actually a test in a vacuum chamber with lunar simulant with these instruments. And what's showing is it's drilling in bites and out comes the pile. And the Nervus instrument is showing the camera and the band depths of the various water. And in the previous slide, I showed what M Solo was doing. So these three instruments together are going to give us that vertical profile of what might have been in that drilling pile. Now, so hopefully this all works out, but it is still going to be fascinating what we find. Okay, so I've briefly shown you the rover, the instruments. Here's our lander. The lander is provided by the Astrobotic company in Pittsburgh. They're part of the CLIPS. They're flying their first lander to the moon later this year. Our landing date is in November 2023, so next year. But it's going to park us to within 100 meters of where we need to be. Since we're a rover, we can live with that because we can replan our path. But where are we going? So this has been an incredible labor of geometry, and Ross Beyer has a paper in the LPSC this year about the site selection process. So you have to land where the sun will be in a favorable position to power our solar rays. We have to be able to have comms with the Earth, so we can't be on the far side. We have to have a reasonable terrain. Here's showing the elevation from Lola, but we have to make sure that we're not going to hit many slopes and other obstacles. And we also need to visit a lot of these where the water ice can be. So several attractive places that Artemis is looking at. Artemis, the human lander program, is looking at Shackleton. They didn't meet our list for communications. Now, if the gateway were in orbit around the moon, that would go away. But in the absence of having a gateway, which is an orbiting space station or a relay satellite, we really had to be direct line to Earth. The steep slopes. Our rover is the first of its kind on the moon, and it's designed to navigate some terrain, but it's not an ATV. I mean, next generation, yeah, sure. So anyway, we narrowed it down to 3 regions: the Haworth region, the Nobile region, and Shoemaker. And it all came down to, do we have enough time on the surface before the sun sets for real for us to measure the density of 10 to 15%, the 3,800 square meters, the 5 types of, the different types of ISRs, all these constraints from a measurement point of view. And Haworth and Nobile fit the bill. The Nobile, a high level on Nobile gave us a little bit longer mission time. So that's where we're going. So the mission area that we're landing is on the western ridge of the Nobile crater. It's a 5 kilometer by 5 kilometer. Caleb Fassett also has done a study on the history of this, the geological age from the cratering statistics. We are targeting an area that's got a range of ages. So we hope to we're going to visit some big PSRs that should be giga years old. There should be 100 million years. And then with the hope of how gardening has happened on the moon, we think there should be lots of younger, fresher craters. So one of the big questions is volatiles and how they're related to the age of the terrain. We think this area covers samples a large range in time. So I talked about ice stability depths. We've now translated that to an ice stability region. We needed a concrete way to kind of communicate a sampling method. And so following the fact that there might be this water cycle on the moon, we have designated this ice stability depth into 4 regions. We have something called the surface, which is indicated by red in our maps. And those are our surface frosts. That's the permanently shadowed region. We have the shallow, shown in green, which is where the ice is possibly stable between the top and 50 centimeters, just in the top. This is the area of active research. This is the matter, is it desiccated down to 20, 30, 50? And then we have the deep, which is the extent of our drill, down to 1 meter. So deep is where water ice may be present, from 0 to 100 centimeters. And this was also a natural cutoff for where ISRU excavation made sense. Now, Matt Siegler and Kevin Cannon and others who do this work, they have certainly predicted that there might be ice at 6 meters deep, several kilometers deep. We're just not going that fast. So this VIPER mission is just sampling that first meter, because there's a region which we call dry, which is shown as gray in our maps. This could either mean no water at all, at least no water on the top meter. It could, there could be water below our sensitivities, but we're discounting that for now. So the science team right now is very active in finding traverses, paths that the rover will take to meet our science requirements. And we have a reference traverse that we're exploring options off. And they have to meet all the parking the rover in the sunlight when the Earth goes below the horizon, so we sleep to live another day. There's time in which we're going to go into a shadowed region and have enough time to do a drill and then come out again and find sun to repowerize our instrument. So we need to find this path, and that this is indicated with the dark green. So the yellow, the lighter green circles are representing radius from a potential landing site. There's several landing areas looking at, because you can imagine starting your traverse wherever you start affects where you wind up. So this particular one lasts about 91 Earth days, and we cover about 13 kilometers. We think the rover can probably go 20 kilometers in distance, but it all depends upon how much time do you want to spend drilling. If you spend drilling, you're not roving. How much time do you want to spend roving? How much time have you spent roving in a slow speed versus a fast speed? So this one met the criteria, and it visited 2 large older PSRs. Again, this is about 5 kilometers by 5 kilometers. That outermost circle is about 3 kilometers from the landing site. So this is where the science team is right now, playing with different types of traverses and ranking them scientifically, and also being reactive, because, well, say we're landed 100 meters this way, maybe we would approach this PSR from a different point of view. This is also kind of exciting, kind of verging on the theorist on steroids, but it's got some ground truths. We have this high resolution planning product. So the previous slides I was showing you are showing thermal maps at 4 meter scales, but Matt on our science team is going an order of magnitude finer scale to 4 meters. And the same colors are the same, but what we're noticing is the predictions are a little bit more fractal. And the moon is going to be its own map to ourselves. The reason why the 4 meter thermal maps are becoming attractive is because we now have 1 meter DEMS to replace our 5 meter DEMS. And I encourage you to look at the 1 meter DEMS for Hallworth that Ross and company made. It's on the PDS Annex. He's taken the LOLA data and he's actually done another, like go from 5 meters to 1 meter. And now you have a higher resolution of the topography. Topography is shading, light and shadow. Light and shadow translates to temperatures. So with the 1 meter products for our mission area, we've now been able to make 4 meters. And this has greatly affected how we define this measurement area of 3,800 square meters. It's really giving us a headache. So here's where scientists are suffering from too much modeling. because what's interesting is the traverse paths that worked well for the 40-meter products are breaking apart for the 4-meter products, because we're going in and out of dry a lot more than we think. And so we are having confidence that the 1-meter DEMS are of high fidelity by looking at other test samples on the moon surface and checking out this photocolumnometry. So these high resolution planning products are certainly the very attractive, but make me pause that maybe are we overthinking the problem? But we have to be dynamic and flexible, and this is the best information we have to date. Okay, to sum up, I entitled the talk Leaps in Understanding of Water on the Moon. And in a public version of this talk, I actually focused on the leaps of water on the moon. And the first came out with the first actual looking at the moon with a telescope, Galileo. He drew the moon and he noticed that the moon had craters and it had mountains. And then we had the erroneous 17th century Western astronomers who called the mare seas, which weren't to be water, but you can see where I'm going with this. But we had the first kind of realistic mapping of the moon ever. And if you're an art buff, you should go and look at how the moon is depicted in art prior to the 16th century to see how funny it looks, because no one had looked at the moon with a telescope. The next leap in understanding of the moon was the physical exploration of the moon in the 60s and 70s, where we put footprints on the moon. We drilled, we dug, we learned a lot, and we still thought it was dry. Then in 2009, we have this explosion of, oh my goodness, cold traps, water cycles. Water can be stable on the moon. And so the next leap is to move towards a proper mapping to ground truth, not just the orbital assets, but then our theory that's leading our way on where the moon. So final slide is about moon water. So these past decade of just keeping up with it, it's been fascinating. We are rewriting textbooks, but we still don't know what we're seeing. It's complicated. Not all the data sets match up with each other. Why you should have one condition and it shows, it leads to different conclusions. So we think there's frost, probably buried icebox. So there's water everywhere. Water is everywhere, but its distribution is very uncertain. So we're going to use a surface asset. We need to get back to the surface. Using mobility gives us an approach to map out a lot of area just to get a ground truth on that. This has got to be followed up with another rover mission, and perhaps Artemis infrastructure will allow more of these. So VIPER is that mission. So it's going to be this first step. It's going to map the volatiles on the moon. We're going to the Nobili region of the South Pole, launch date November 2023. The mission should last about 100 days, because at that point we get out of summer solstice into where the shadows are way too long and our batteries will drain. We can only stay about 50 hours in darkness. So an interesting trait on the story is, how should our mission end? Should we park ourselves up on a high mastiff and be bathed in the sunlight, and then at some point the shadows will drain our batteries, but then someone will come and find us? Or should we drive deep into a permanently shadowed region and just get as much data as we can? And then hopefully someone will find us in the dark someday. Thank you.
Okay, thanks so much. We have time for a very few quick questions, if anyone in the audience. Why don't we start there?
Thank you for interesting talk. I have a question about the age of craters. You talked in a latter part of the talk. So I think this is the point to be investigated. But are there any theory which younger or older craters are good for investigation or exploration of water?
Okay, so the question was about the ages of craters and whether there's a preference of whether older or younger craters are. Well, that's what we want to look at, both older and younger. Because if it's older, it may indicate that the water ice on the moon is old and ancient and may have told us about the history of our solar system and perhaps the history of our oceans on our planet. If water is present in more younger craters, this could tell us that it's a more dynamic and more active and more present day activity and not something from the past. Maybe it would indicate whether, is it being moved around or replenished or in some way. So we want to look at both, not just old and not just young, but a range.
Thank you. Yeah, thanks for your talk. That was very interesting. This is kind of building up of that question, but you were talking about how there are these 3 different types of water, like the in situ versus produced there. So can you actually tell the difference between those with VIPER?
No, we can only tell whether it's there and how much of it is there. We won't be bringing back samples. We won't be digging into rock. We'll just be, digging from beneath. If it's, we'll look to our theorists to perhaps explain where it could be. One of the things that the drill wants to do is distinguish whether the ice, because we don't have a microscope to actually look at like ice grains or anything like that. So we don't have that kind of knowledge. We're just going to have to look at physical parameters and make some assertions. Oh, that must be incorporated with soil around it. And then it means, oh, it must have been implanted. So there's going to be many steps. So we won't be able to distinguish the sources of the water. We'll just tell you what form it's in, whether, and then and where it is and how much of it is.
Thank you for the talk. More than 50 years ago, believe it or not, I wrote my first scientific paper on the thermophysical properties of the lunar surface. Interested in porosity and thermal conductivity and such. And I actually did reading of opacities of various minerals and whether they have water vapor or not, just looking into how the soil might be done. Of course, that's many years ago. But one of the things that I think that came out of that, I was just thinking about it, was that you might be able to learn a good deal about the presence of water in the soil very locally from essentially a mission that in orbit around the moon that does millimeter wave spectroscopy. So I would think that would be an interesting thing to do before you actually send VIPER there.
Well, thank you for that. Yeah, the suite doesn't have all the bells and whistles that it needs. I wish it had a ground penetrating radar, for example, or it had some more precursor missions. But the VIPER data set will have a legacy. So if future missions can do the submillimeter and the orbiter micro, the sounding, we could probably interpret the VIPER data.
Any last ones? Did you still have one, Mitch, or you're good? Okay, then let's wrap up. I won't keep you over time. Thanks again.
Thank you for the opportunity.
And we do have one more spot for dinner tonight, I think. Early bird dinner, 5:45 at Salt. If anyone wants to join, just come find me or shoot me an email. You can join for a drink and take off if you need. Thanks again.